Okay, picking up where we left off, in this next video we're going to talk about page 2 from Homework 11 Extra Problems. And page 2 starts with example 11.04. A hydraulic car lift consists of two interconnected cylindrical chambers filled with fluid. And the circular areas are given to us as radius 1 and radius 2. The car is placed on the larger piston, and the combined weight of the car and the piston is 20,500 newtons. So that's given to us. It's on the larger one, so we may label that as weight 2 if that helps. Or better yet, we might even call this force 2 instead of weight. We'll just call it force. And our job is to determine what force F1 must be exerted to keep the bottoms of both pistons at the same level. So what we have to keep in mind is that let's say there's a piston over here on this side, and it's connected, its fluid's connected to another piston on this side of the system. The level, let's see, effectively these piston arms can raise and lower. The level of these pistons want to remain consistent if the pressures on both sides are the same. If we've got moving fluid, then we could raise the height of one piston and drop the other, but that would create an imbalance in pressures. So we want these two pistons in this particular problem to be on the same level. We'll maintain the pressure. So we're going to find the force necessary in order for pressure 1 to be equal to pressure 2. And we'll also note that pressure is equal to the amount of force that's being applied divided by the area over which the force is being applied. So since F1 divided by A1 is pressure 1 and F2 divided by A2 is pressure 2, we can isolate F1 by multiplying both sides by A1, and then we can sub in our values. The only catch here, of course, is that we weren't given an area to begin with. We were just given the radius of each piston. So we'll multiply pi times radius squared in both cases, and the end result comes out to be 32.8 newtons of force. And so I would argue that's pretty impressive. Only 32.8 newtons of force to support the weight of the vehicle and other piston that has a weight of 20,000 newtons. So the next question, 11.05, we're being told that we have a mercury barometer. Now a barometer is a tube, and it's since it's a mercury barometer, it's filled with mercury. So we've got this tube, if you will, filled to the brim with mercury. It's flipped over and then placed inside of a pool. So we fill it with mercury so that there are no voids here. It's completely full with fluid, and then when it's flipped over, it's upside down like this. The pool of mercury tends to come out just a little bit and fills the rest of this area here. And we've got an empty kind of a cavitation of space towards the top here. This vacuum is, or empty space is going to create a vacuum because the weight of the mercury wants to fall out of the tube, but then there's pressure, atmospheric pressure outside of that tube pushing this pool of water back down until it equalizes at a particular position. And the image from our textbook looks more like this, so hopefully that makes a little bit more sense and it isn't quite so sloppy. So we've got the pressure that's pressing down from the air, so atmospheric pressure, ATM, I'm going to call this. And we've got this vacuum that's created because the weight of the mercury wants to pull out of that tube, but it can't because it's the weight force is being resisted by the atmospheric pressure. And so we'll note here that our job is to find the pressure associated with the mercury, and it's not pressure at depth, so we're not talking about pressure beneath the surface of water or something like that. There's only one pressure that's working here, that's atmospheric pressure. So the pressure is the result of the density of the fluid times gravitational constant times height. Well, again, we're in equilibrium, so the pressure that we experience is atmospheric pressure, 1.01 times 10 to the 5th pascals. The density of mercury, 13,600 kilograms per cubic meter. Earth's gravitational constant times h. We can solve for h and obtain 0.757. Now that's a measurement, of course, in meters. We can convert that, and if there's some rounding involved, we might end up calling this 760 millimeters, and that's the pressure that we're experiencing, millimeters of mercury. So that's actually a unit of measure that's equivalent to 1 atmosphere, or also 1.01 times 10 to the 5th pascals. Now the next example is kind of an interesting one. We're being asked how high can this pump actually pump some water out of a well, and the diagram that's supplied to us kind of describes the problem, and it introduces a situation that you may or may not be aware of. We've got a pump that is placed into some well, and it's trying to eject water out of the well and onto the surface, and they've actually drawn the pump up here. And what may not be clear at first is that this pump is using what's called an evacuation method, and it's effectively creating a vacuum in order to lift or to create an imbalance in pressure. So this vacuum is created in the pipe, and it's creating imbalance in pressure so that the pressure from the atmosphere pushes down on the water level and then effectively pushes the water out of the pipe. So the limiting factor on this particular pipe is that, well, it can only create this vacuum by evacuating all of the air. Therefore, the pressure that's used to push this water through the pipe is effectively only equivalent to the atmospheric pressure that we experience at this particular point. So if our job is to determine the height of the water that can be evacuated, well, we know that the pressure of the atmosphere is equal to the pressure of the water inside that column, and the pressure of the water in that column can be found by computing its density times G times H. And if we isolate H by dividing both sides by rho and G, we end up with this computed result at the end. Our air pressure in pascals divided by the density in kilograms per meters cubed, and our gravitational constant in meters per second squared. That generates a height of about 10.3 meters, which is about 33 or 34 feet. This is a fine pump for, say, some pumps in your house, but if we need larger pumps in larger systems, then different pumping systems have to be developed. Okay, and in example number 11.7, we're being told that a solid pine box with the density of 550 kilograms per cubic meter is placed in a pool of water, and we want to know if that box will float. Well, a box will float if the density of the item is less than the density of the water, and that is true because we have 550 kilograms per cubic meter, which is less than 1,000 kilograms per cubic meter. And as we discussed in class, the portion of the box that's submerged is simply a ratio of densities of the least dense or less dense object to the more dense object, and we have 550 divided by 1,000, so that tells me that about 55% of the box is submerged, so about half of it will be under water when placed into that pool. Now the amount of the box that's submerged is really a question of force, but we learned that the ratio of densities will also generate the same result when we, as if we had actually converted into forces. Now, regardless of whether the box floats or sinks, there's always a buoyant force acting on an object that's placed in the water, and the buoyant force of any object in water is equivalent to its weight. So this buoyant force is the upward force due to density of water pushing back on the density of the object, if you will. So in this case, the buoyant force on the block is equal to mass times gravity. Now mass is equal to the density times volume, and we've got a density of 550 kilograms per meter cubed. We're being told that the box itself had a volume of 0.85 cubic meters, and so therefore when we multiply the density times volume times gravitational constant, we have this upward force pushing on this box at 4,586 newtons. And so the last thing that I'll say to this is that if we're wondering how much stuff we can pile on top of or inside this box, well, we would, or before it would sink, that is, we'd want to know what the total weight of the box and all of its contents are When those two are in equilibrium, then the box will be floating effectively right at the top surface here, and that would be the maximum amount of weight that it could support. So if we wanted to go through those conversions, we could determine the payload, if you will, of that box. Rather than stopping the video now, we'll just go ahead and finish the last question in this particular set. We're being told that ice has a density of 917 kilograms per cubic meter, which is why it floats in water. And the question becomes, well, if we had a glass of water and it was filled to this particular level, we know that when we drop ice cubes in there, the water level can change. But the question becomes, what happens after the ice cubes start to melt? Now, we're going to drop these ice cubes into the water, and we'll notice that the water level had to increase a little bit because there's a portion of the ice cubes that are submerged, and that's displacing water in this vessel, so therefore the water level had to rise. But what's going to happen as these ice cubes start to melt? What's going to happen to this water level? Well, as it turns out, the water level is going to remain constant since the weight force of the solid water, the ice, is displacing the same weight of the water that caused the initial rise. So after we drop the ice cubes in and we see this rise in water, the weight associated with this particular volume of water stays the same. So as this ice, as the solid water changes its phase to liquid water, the weight remains the same, and the amount of water that's displaced ends up remaining the same as well. Now, if we had a cup, let's say, or maybe a bottle or something like that, that had water filled up pretty high, and we put a lid on top of it, pushing the ice cubes below the surface of the water, well, now the ice cubes are displacing more water than before, so the water level may have risen a little bit, or may have risen a little bit higher, and now as the ice cubes start to melt, the water level will actually fall. And that's because the density of the solid water, the ice, is less than the liquid water. It's displacing more volume for the same amount of mass. And so you can think of it another way, that in this case, since it's a solid that's taking up more volume, it effectively shrinks as it melts. And as this shrinks, it allows the water level that it had displaced to actually fall. So I think that's a good stopping point for this video, and that completes the full set of extra practice problems from Chapter 11, Static Fluids. I'll continue with one more video on the questions, extra practice problems from Chapter 12, having to do with our fluids in motion. Thanks for watching.